Hello, calculus fans. We're going to talk about computing surface area. We'll use double integrals to compute those areas. We're going to solve two types of problems. First, we're going to talk about how to compute the area of a parametric surface. And then we'll talk about how to compute the area of the graph of a function of two variables. And we'll use the setup for the area of a parametric surface to get this second one. All right, so to start with, I would like to remind you that we have defined what we mean by a parametric surface. That is, we have a surface that's given to us by a set of parametric equations. Here I've written it in vector form. So the x values are given to us by some function of u and v, same for y, same for z. The u and v are the parameters. You don't literally have to use u and v as parameter variables. You can also use other variables. In some circumstances, we've used, for instance, phi and theta when using spherical coordinates, and we'll talk about doing that. So we can represent these with parametric equations instead of a vector form. And of course, u, v will vary throughout some region D, and we'll have some way of expressing what are the bounds on the u and the v. Now what we're going to do is we'll take the surface S and we'll divide it into patches, and we'll approximate the area of each patch by the area of a piece of a tangent plane. Now remember that we've talked before about how to find tangent planes to parametric surfaces. We didn't do a huge amount with that, but I'd like to remind you now how we did that. And we remember that if we make this vector n, which was RU cross RV, and just to remind you that when we talk about these guys, we're talking about the derivative of the vector function r with respect to u and with respect to v. As long as this vector is not 0, then we're going to say that the surface is called smooth. And then this vector here, n, is a normal vector to the surface. All right, let's now define the surface area of a generic parametric surface defined by this vector equation. Let's make a simplifying assumption that the region that we're integrating over is a rectangle. And of course, we have ways of fixing things up when it's not a rectangle. For instance, when we had type 1 or type 2 regions. So what we do is we divide our region D into subrectangles, and then we can choose a sample point on the lower left corner of each subrectangle. Here's a picture. So what you see on the left over here is our rectangle that's being divided up, and then over here is the actual surface. So when we divide the surface up, these are not exactly rectangles. We'll see that in the next picture. So the part of the surface S that corresponds to the rectangle is called a patch. It's close to a rectangle, but is not exactly a rectangle. This patch has the point Pij as one of its corners. We can use the vector r of ui star vj star as a vector pointing to one of those corners. And then we're going to define RU star and RV star. These are the derivatives evaluated at this corner point. And now let's look at this next picture. What you see is that the patch, which is Sij, is pretty closely approximated by the section of the tangent plane that we get from the tangent vectors at those points. The picture is showing us that the two edges of the patch meet at the point Pij, and those edges are approximated by vectors. And the vectors that we get are delta u r sub u star and delta v r sub v star. And that's because the partial derivatives can be approximated by difference quotients. All right, so let's get to the upshot here. What does this mean? We can approximate the area of Sij by the parallelogram that's determined by these two vectors, delta u r sub u star and delta v r sub v star. That parallelogram lies in the tangent plane to S at the point Pij. Well, we know how to compute the areas of parallelograms. We just take the magnitude of the cross product. And that gives us a very nice formula for the area of this parallelogram. So it's the length of Ru star cross Rv star times delta U delta V. And so if we want to approximate the total area of S, we can do so by summing all of these. And this is a double Riemann sum. And if we take a limit as m and n go to infinity, what we get is a limit of a double Riemann sum. And that tells us that the area can be represented by the integral that you see here. So let's make a definition for the area of a parametric surface. So let's suppose that we have a smooth parametric surface given by this vector function. And let's suppose that the surface is covered just once as u and v ranges throughout the parameter domain D. Covered once means that any particular point on the surface corresponds to one particular ordered pair uv. Then we're going to say that the surface area of S is defined to be the double integral over D of the length of Ru cross Rv. And of course, Ru and Rv are just the derivatives of R with respect to u and v. Okay, that's all for now.